All right, grade nines. Well, welcome to me explaining significant figures to you. Look, I actually wanted you to try reading this on your own, just to see how you would do. Okay, so I'm going to explain this to you and give you a couple of examples. It's pretty easy once you get the hang of it. Very important thing. I know it's not the most exciting thing in life, but I'm trying to think of useful things for you in the future. So, for example, in grade 10, grade 11, grade 12, in science class, especially if you're in Mr. Ruddy's chemistry class one day, you will very much appreciate understanding this. Okay, so it's something that grade 9s should be able to do no problem. The math isn't really that difficult, but and it has everything to do with how measurements are made in science. Okay, so I'm going to go over these rules with you, and then I'll take a few minutes and just look at the other sheets that I've assigned to you as well. Once you understand what you're doing, it doesn't take very long. Okay, all right, so significant digits. Okay, first of all, any digit, like when you're looking at a number, any digit that's not a 0 is always significant. Okay, so really this is all about what you do with zeros. Okay, if there's any non-zero digit, it's always significant automatically. Okay, and so that's easy to remember. So that takes care of all non-zero digits. Okay, now zeros that occur between non-zero numbers are always significant too. Okay, so rule number 1, okay, any non-zero digit is significant. Okay, so I'm just going to sort of check these off as we go along. I don't really need to write them again. That means like any number, 1, 2, 3, 4, 5, 6, 7, 8, 9, any digit like that that's in a bigger number always counts as significant, right? So non-zero digits, always significant. Okay, zeros between non-zero digits are always significant too. Okay, so to give this example here, 5007 has 4 significant digits. Those 2 zeros right here are significant. Okay, now trailing zeros are kind of interesting. A trailing 0 we consider what's called a placeholder. So for example, if I want to write the number 5,000 down, okay, so if I write this number 5,000, see, the thing is there's no way for me to write, if that number only had one significant digit, okay, like just the 5, there's really no way for me to write it without the trailing zeros if I want to write the number 5,000. So these zeros here that I'll just circle in red, those zeros are placeholders. Okay. In other words, they are there so that I can tell you what the size of the number is going to be 5,000. There's no way for me to write 5,000 with just the 5. I have to include the zeros, right? Now, if you're wondering why, maybe this sounds a little strange to you, it's like, think of it like this, okay? Let's say if I asked you to go outside and estimate how many blades of grass there are on like 10 square meters of field, okay, and the soccer pitch or something like that. Well, there's a lot, right? Okay, there's a lot of blades of grass. So you might throw out a number. You're not just going to guess. Maybe you make a measurement of a small section of it, and then say, all right, like I measured this 10 square centimeter section, if I'm just going to multiply it out. Okay, now when you do that, you're estimating. Okay, so because it's such a rough estimate, you're just going to round it off to the nearest 1,000. So what you're telling me is the number is very rough. It's not very precise. So that's what the one significant digit means. It means that you're getting around 5,000. Now maybe the real number is 5,225 blades of grass, or maybe it was 4,783. But it's such a rough, you just estimated it. You're saying, look, it's approximately 5,000, okay? I didn't count them all. Had you counted every blade of grass, then all of these digits would be significant, okay? And you wouldn't write it this way. You would put a decimal point at the end to say that you counted them exactly and every one counts, okay? So in this case, if I don't write that decimal point, those zeros don't count. They're just placeholders. I say the number is around 5,000, So you can say like, how many fans were there in the stands? Let's say around 5,000, right? Before the, some game somewhere before the outbreak happened. Okay, so trailing zeros are significant only if you have a decimal point. Now, this is kind of weird, but if I want all those numbers to count, like let's say I count the number of blades of grass and I got it down to exactly 5,000 and I want to show you it's exactly 5,000, well, I would have to write it like this. It's exactly 5,000. Now, normally having a decimal point, okay, so this number has one significant, I'm going to write significant figure, 1SF, like that, okay, and the placeholders don't count. But if you put the decimal, then what you're saying is you counted whatever it is you're measuring, you measured it and you got exactly 5,000. So that means these zeros were actually measured and they count, therefore they're significant. And this has 4 significant figures, okay? All right, so if you look at their 2 examples, the number 100 only has 1 significant digit, no decimal, and therefore the trailing zeros are only placeholders, so therefore 1 significant digit. But 100.0 has 4 significant digits because all of these numbers, I wouldn't write decimal 0, if I didn't measure that number. So you're saying you got exactly that. Let's say I was measuring the temperature of boiling water, and my thermometer, I looked exactly and read the number exactly off the thermometer, and I got exactly 100.0. It's right on the dot, right on the measurement, okay, 0.0. Otherwise, I wouldn't write the 0.0. I'd just say, well, it was around 100. And if I do it like that, then I don't write the decimal. Now, these 2 numbers are equal, of course, right? So look, these 2 numbers are the same number after all. Okay, they are equal. It's just the thing is by writing it this way, what you're doing is saying that you measured all the digits. And so they're all significant. In other words, all of those zeros were measured values. Here was a very rough estimate. This number here, I'll circle in blue or underline in blue. That one there, you only measured the first digit and you sort of estimated it was around 100 for the rest. You didn't precisely measure it. If you did, you would have put a decimal place. You get it? So that's sort of where this comes from. I know it seems kind of strange. We're not really talking about doing any measurements here. But as long as you sort of get the rules, we'll talk about measurements later. Okay? So anyway, zeros, like leading zeros, I call them, okay, in decimal numbers, are placeholders too. Okay? So let's do this example here. So this is rule number 4. These are called leading zeros, these 3 zeros here, but they're placeholders. Okay, so they're not significant. Just like trailing zeros in numbers without decimals are just placeholders, these are also just placeholders. That's a really small number, 0.0025. Okay, so let's say you're measuring in meters or something, that's just 2.5 millimeters. Okay, and what you're saying is that this measurement only has 2 numbers that you actually measured, but it was a small measurement, so these other ones are just there for placeholders to show you how small the number was you measured. Okay. So that only has 2 significant digits. That makes sense. But trailing zeros in a decimal, you don't have to write. Okay? So for example, this number here, I call it a trailing 0. I'll rainbow the trailing 0. That trailing 0 is unnecessary. That's not a placeholder that we need to write, right? So if I were to drop that, let me cross it out, that number, 0.0047, and this number, 0.00470, are equal numbers. They're the same number. Putting that trailing 0 doesn't change the value of the number, okay? But what it does is you're saying that you measured this 0, okay? This is significant because why would you write it otherwise? You don't have to write that number. You don't need to hold that place. These zeros here are holding the place. They're placeholders. You have to write those to show you how small the number is, but you don't have to write the trailing 0. You only write it if it's significant. In other words, if it was actually a measured 0. Okay, so I tell students, like, significant digits, it's all about what you do with zeros. Okay, that's sort of I can summarize it for you. So I can sum it up for you like this. Non-zero numbers, you get it, they're always significant, right? Zeros in between numbers, always significant. Those are the two easiest rules. Okay. Trailing zeros with no decimal, never count. Okay. And trailing zeros with a decimal, always count. And the last rule, leading zeros, never count. Okay. Leading zeros never count in a decimal. Only trailing zeros can count if there's a decimal. Okay. So anyway, that summarizes the rules for you. Now, if you want, we can do a couple of these together. Like I said, it doesn't take long to do this homework. I could add another rule. You know what? I should add this rule also, but it's easy to remember. Scientific notation, which we covered before. In scientific notation, every digit always is significant. Every digit is significant. I don't know if it comes up in the assignment, but in fact, that's why we write numbers in scientific notation, just to make it simple for everybody. So all the zeros, whatever the zeros are, they count. That's it. Scientific notation, every digit is significant if you put it in proper scientific notation, that is. Okay. All right. So now we're doing these questions here. This is 1, this is 2, this is 3. And you see how quickly I'm doing that? Okay, this would be 4, this would be only 1. Okay, but you see this little decimal here, that makes that one have 4. Okay, here, because these trailing zeros don't have to be written, every digit counts. So that'll be 4, 5, 6. This is only 1. This is 4, and that is 5. Okay, so if you get it, see how quickly I did that, right? It took me less than a minute. Like, once you understand the rules, it's easy. Okay, now determine the location of the last significant digit by placing a bar over the last digit. All right, so I'll use my rainbow color. That's the last significant digit in this. Oh, it's not working for some reason. Okay, in this case, it's this number. Here, I'll fix that. It doesn't want me to fix it. Oh, there we go. All right, this one. All right, scientific notation, all the digits count. Okay, this one here, sometimes it's just the last digit. Let's work our way backwards here. This number here, 000410, that one. This is in scientific notation, so they all count, all 3. This one, this is the last significant digit. This one here, and that one there. Okay, so again, it only takes a few minutes to do questions like this. So there's your answer key for page 1. Okay, now, unfortunately, it's that the story doesn't end with just being able to recognize how many significant digits are in a number. What do you do? Like, let's say, for example, we were to go back to semester 1, and I don't know if you guys remember, but we did a density lab where I brought out these blocks, and you measured the length and width and height. Okay, and then you also measured the mass, and we did mass over volume equals density. So what we did is we made some measurements and we did some calculations. And my point to you is this. The whole point of this is like, see, in science, and some of you may be working in scientific careers in the future, in science, when you're making measurements, it's really important that whatever it is you're trying to determine in your lab, you can't state a value in the final sort of result of your lab, okay, that's more precise than your measurements were. Okay, so that's the point, is that you get that notion. Okay, so let's say, for example, I measure like here, I'm trying to measure the volume of a cube, or not a cube, but a rectangular prism. So here it's 23 centimeters by 432 centimeters by 19. Now look, how many significant digits are in this number? Well, there's 3. How many in this number? 3. How many in that number? Only 2. Okay. And so he's got these 3 measurements. 3 of them have 3 significant digits, but that guy is has the least precision. Well, if you like, it has the least number of significant digits. And so your answer here, he has 6 significant digits there, okay, in his calculation. So he just pulled out, this is what students do, right? You pull out your calculator, just multiply these 3 numbers together. That's the number you got, right? But wait a second, you can't have that kind of precision in your answer when you have one of your measurements which was quite small and therefore not very precise. Okay, so you have to take this, the answer, we have to round it to 2 significant figures. Okay, because of the one I circled only has 2. And so we have to round this, and if we're only going to keep 2 significant digits, that means just those first 2. But you know, I'm going to take in consideration, I'm going to circle it in red, these 4 digits here, because when I round it, so I got 18 and the next number is an 8, so I have to round that up. That 18, I round it up to a 9. So now this number is 190,000 cubic centimeters. That only has 2 significant figures. Okay, and I have to make it that way since 19 was my limiting number that only had 2 significant digits in it. Okay, so when you're multiplying or dividing, okay, or taking an exponent, so this rule here, okay, it doesn't matter if you're multiplying, dividing, exponents, you know, square root, you know, whatever. Any operation like that, you use this rule. So say, for example, I'm trying to find the hypotenuse of a right angle triangle, right? Like a squared plus b squared equals c squared. Well, I'm squaring my numbers and then taking the square root of the final answer. So the deal is whatever measurements I make, I know some students will get confused with the addition and subtraction if they're mixed steps, but what you do is your final answer can't have more significant digits than your measurement that has the fewest, right? Okay, so, and don't worry, we won't make it too complicated for you in grade 9. Okay, so now look, when you're adding and subtracting, it's a different rule. What we do when we're adding and subtracting is we go by the number of decimal places, not the number of significant figures. So this number here has 2 decimal places. Okay, this one here has 1, and this number here has 3. Okay, so the rule is this has to do with precision. So the most precise number has 3 significant digits. So let me circle it for you. This one here is the most precise, but this one here, with I'll circle in red, is the least precise number. See, one of them was measured to 3 decimal places, but this one's only measured to 1. Okay, so that's 1 decimal place. And therefore my answer, I must round, that has 3 decimal places, but I must round to 1. Okay, so 1 decimal place, so 255.507. 0.7, I would round that down, right? If you like, you could round the 0, you can round the 7 to a 1, but then, you know, 255.51, you would round down to 255.5. So now we look at this. When you're adding and subtracting, this is your rule. Okay? Now I know this is all written down for you already. That's why I wanted you to read the notes. Okay? All right, now some of these questions are a little, they're mistakes. Okay? So let's fix our mistakes in this question. I got the sheet online, and so if you look at the answer key, please ignore it. I don't know if that was a student's answer key or what, but anyway, some mistakes in it. So look, what you do when you're doing these questions, you use a calculator. Number 1, use a calculator. This isn't an exercise do I know as a person how to add, subtract, and multiply, okay? Yeah, you can do it in your head if you want, but you know what? I'm going to use my calculator, and I'm just going to say 1.35 times 2.467. All right, Now my calculator tells me that this number is 3.33045. But I have to use, I just multiplied those numbers. This has 3 sig figs, and this one here has 4. So I have to round that to 3 sig figs. So that, okay, has 3, and that is my answer. Okay, now by the way, there's a unit. You're multiplying, so it would be square meters. Okay, meter times meter would be square meter. Now I'm going to point to you a mistake, okay, that they've made on the sheet, and they've made it a couple of times. I don't know what they're thinking. You can't mix and match units when you're adding and subtracting. So let's fix that right now. That has to be meters also. It doesn't make sense to add meters and square meters. It's like, you know, it's like adding a square and a straight line. Like, how do you do that, right? So forget that. It's a mistake. So this number here, it's adding, right? Now they both have no decimal places. So like in this case, because we're adding and subtracting, 1035 plus 42 is 1077, and all of those digits would be significant, and this would be meters, would be your answer. All right. So is that? Hopefully that makes sense to you. I want to show you this one also. I don't know if they meant to times these. Their answer that they had in the answer sheet makes no sense at all. Ignore that, please. Okay. And I tried to. I raised it on OneNote, but if you double clicked on the icon, answers will show up, but some of them are incorrect. Okay. All right. So now, what about this? Okay. And by the way, we are going to have a test on this, like a quiz. So we'll do it early next week. I think I mentioned that before. So now here, 12.01. I don't want to do the whole thing for you. Plus 35.2. I'll just post the answers later. Plus 6 equals 532.1. No, that's not right. 12.01 plus 35.2 plus 6. 53.21. Yeah, that makes more sense. Okay, so I get 53.21. But this has 2 decimals, this has 1, and this has no decimals. So this has 2, this has 1, this has 0 decimals. So therefore my answer I have to go by my limiting factor when you're adding and subtracting. That has no decimals, and so I must round my answer so it has no decimals. So that would round off to 53. Okay, and the unit stays the same when you're adding and subtracting. It only changes when you multiply, okay, or divide or whatever. But in this case, adding and subtracting, the units stay the same. All right, I'll let you do these other ones. There was another mistake I wanted to point out to you here. 2 more mistakes. So let's get rid of this. Okay, it's just 150 liters. This is simple, it's 154 liters, right? And I don't have to round it at all because they both have 0 decimal places and I'm adding, okay? The other mistake I wanted to point out was this guy. All right, so here you're adding, so you just go ahead and add them, okay? You know what, this one's a bit tricky. Let's do this one together, it's number 10. Okay, and I was just thinking about it as I'm looking at it. You need to convert this into a regular number. So what's 1.278 times 10 to the 3? Well, just multiply it out. This is 1.278, okay? Plus, this one here, if I multiply by 10 squared, I'm going to move the decimal place over 2 spaces. Remember we did scientific notation before? And I get I get 142.67 meters. Now, why did I do that? Well, to see how many decimals I have. Here I have 2. Here I have 0 decimal places. So I just add the numbers up, and how many decimals do I keep? Well, I keep 0. So that's 1.278 plus 142.67. And I get 1420.67. But I have to round that, so I'm going to round it to 1421 meters. Okay, that's it. So hopefully that's helpful. Now I wanted to show you, I wanted to show you one more thing. All right, so what's this all about? Well, the thing is, it's all about making measurements. Okay, so that's what significant digits are all about. Like in math class, they just throw a bunch of numbers at you. But in science, we're making measurements, right? And here's the deal, okay? When you're making a measurement, okay, and like let's pretend you're standing on a scale, or you put an object, and in this case it's too light of an object, and it's too small of a scale for us to measure someone's weight, so whatever, okay? So here's the deal. How heavy is this object? What is its mass? And here's how you would read this scale. This number first, 500. Then we're going to add 70. And then we're going to add this. Okay, so it's 577, but I can do better than that. This number is between 7. I'm going to zoom in as much as I can on this number. Now, here's the thing. This, if I count the tick marks, okay, that's 7.12345 so I'm at 7.6, but it's not quite at 0.7. It's between 0.6 and 0.7, right? So you're supposed to, when you're making a measurement, estimate the last digit. Okay, so I'm going to write that this number is 577.7. Sorry, 0.7. Oh yeah, I'm sorry, 0.7, and I'm going to say that's about, and we're going to maybe disagree on this last digit, but I'm going to say that's another 7 there. Okay, so if I zoom in as much as I can, it's definitely past halfway, but I don't think it's quite at 0.8. Now, you might say it's 0.8. Some people might say it's 0.9, but we're estimating. So this digit here, and this is crucial that you get this digit is estimated. Okay, this last one. And we estimated it right in there. Okay? Gosh. Okay, so I'm going to stop this video here for now because my son has a Zoom call with a hospital. So, all right, so I will maybe continue this in a second video, but I'll leave that for you.